Okay, I think this is working. So this next problem that I want to do is actually the proof of theorem 4.16. It is lined out here by Past Jordan. This is on my like study set of flashcards and everything I did for the first exam. What I found fun is I would write down like down here is the proof. I won't show it to you because A, I want you to see it or not see it and then like experience it for the first time. But the best way that like I found studying was to write it down, then like randomly look at the flashcards and then see this and try and prove it. And then when I was done, I'd compare it to my like exact proof that I copied down either from the textbook or like from the homework, and see how I did and if I was like up to its standards. So sorry, I've rambled on enough. If G is a group with binary operations star, and if A and B are any elements of G, then the linear equations A star X equals B and Y star A equals B have unique solutions X and Y. I think this is a great proof to practice. One of my favorite. Partially, it gets you working with hint hint inverses, as well as how do you show uniqueness. Um, and uniqueness is an important tool in math. I find that it's valuable. So I'm gonna. Can I just? How do I? I'm gonna bring this guy with me to my scratch page. Look at me. Oh, whoa, that's way bigger than I was. How do I make you not huge? Okay, that's much better. So, here she is. Let's get going. So, ooh, I don't want black. I want pink. Proof. Where do we start? So we're given the equation. Um, I'm gonna skip the formality and say like, assume A star X equals B as shown above. I don't want to copy all that out. That's a waste of both of our times. um, uh, without the only way I've ever seen this in the textbook and how Webson would say it is clearly. But I don't like that word. Neither do I like obvious. So how do we want to word this? Um, it can be shown. We'll do that. It can be shown that X equals A inverse star B is a solution. How can that be shown? Well, let's just plug it in for X. So we have A star, and then I'm going to plug in X, which is A inverse star B equals B. Let's simplify that using the rules of a group's associativity. We can then go to A star A inverse star B equals B. And then we get from this, I should be a little more clean. The screen isn't as zoomed in as I normally like. We get E star B equals B, and then we get B equals B. Yay! So A inverse star B is a correct solution to this linear equation. Um, that means that X has a value. Let's do the similar process for Y, and then we'll show uniqueness. So we have assume Y star A equals B. So the quirk of this problem is it like introduces us to something with that you never do in some people would call it trivial mathematics or school mathematics is worry about which side you multiply or add on, right? 3 plus 5 equals 5 plus 3. But as we see with abelian groups, commutativity is amazing but dangerous to assume. So with this introduction to abstract algebra, you have to be careful of where you place this A inverse, right? Because I need it to line up directly next to the A. So there's a reason it's A inverse star B and not B star A inverse. because um, y in this case is the opposite of that. Y will equal b star A inverse because now when I plug that into this equation right here, I'm going to get where my A inverse and my A line up. So let's go ahead and do that. So we'll have B star A inverse star A equals B. And I'm sure you can see how this will eventually get me to B equals B. I hope that me skipping is not too dangerous, but these A's will make you an E and then you'll have B equals B. Um, so now that we've done that, we have that there are some solutions to these linear equations, but how do we know there's not an infinite amount or three of them or none of them? Well, we did show none of them, so we've got that start. Now let's show uniqueness. And uniqueness always has the same approach to it every time, or at least that I've seen. To be fair, this is coming from, an undergraduate, so maybe I shouldn't be talking like I'm the de facto ruler of this type of proof. But when in this class previously, when you show uniqueness, you assume that they're not unique. So assume x1 and x2 act as solutions. Then we'll have from our equation a star x1 equals b. But we'll also have a star x2 equals b. And by the little law that is known as law of equality, since they're both equal b, we know they have to equal each other. And luckily, that's something we can still conclude in abstract algebra. So we know that a star x2, or sorry, x1 equals a, that's a horrible equals. Sorry, I'm being a little like Ada. I don't want it to be sloppy for you guys, but to be fair, it's 12:42 now, and I'm quite tired. Um, Now I believe it's theorem 4.15. Yep. Wow, I've memorized these a little too well. So we've proved this earlier. I can do a video on that if you like, but I'm just going to say by theorem, and in fact, I'm going to be a little pretentious and say the number of it. By theorem 4.15, we know in groups, I'm just going to use GPS, that left hand side cancellation holds. If that's confusing, hopefully I'll like make a video on why that's true with this proof. But that means that we can like cancel these A's. You know what? I'll just show the why that works. If I multiply by A inverse on both sides, um, that's pretty easy to show. Oh, and I forgot my x1. A inverse, ooh, I'm being sloppy. A star x2. So these A inverses cancel and we'll have, so x1 equals x2. Thus, these solutions are unique. I will pull a classic mathematician and classic math professor, and I'm not going to show that this is true for our, where are they? Whoa, where am I? I'm not going to show that this is true for y, but it is true, right? Because I can just plug it in. I'll say y1, y2, and then I think it'll just come out to where I use right-hand side cancellation, which just means I put the A inverse on the other side, which you're allowed to do. And boom. So we have proven that these equations have solutions in a group and that they are unique, which is that they'll always just be the inverse to get rid of it, and then the thing that you want to equal, which is a really cool tool to use. I'm rambling at this point, but thank you. I hope that was useful. Let me know if you want me to do a proof of where is it? Theorem 4.15. It's pretty standard. It's not long at all, as you can see down there. But yeah,